Here is the next example on a delta-delta connection, three-phase. So in this example, he gave us three-phase 120 volt. Remember always that's a line-to-line value, delta to delta. So source is also delta, load is also delta. Connected balanced load has a branch impedance of 12 minus J9. So each branch of the load has 12 minus J9 ohms, and it is a delta load. We can clearly say that or see that. The transmission line has a line impedance of 1 plus J1. So the transmission line is also having an impedance. That value is 1 plus J1. Now the source is also a delta, so I'm going to draw the delta. So the complete diagram is going to be something like this. Okay, so that's A, B, C, A, B, C. Now the given voltage, as I mentioned, it's always line to line. So the voltage given value is 120 at an angle of 0 is right there. Now find the power, active power, reactive power, apparent power supplied by the source and consumed by the load. Now power supply is different than power consumption because of the line impedance. There is some loss in the line. So for example, this power plant or this generating station is far away from your load, then we have to run a transmission line. The transmission line will have some impedance. That's what this 1 plus J1 ohm. Okay, 1 plus J1 ohm. We can solve this example by using KVL and KCL. I always solve this example by converting the given load into Y. That's easy for me, so that way I can find the impedance of the Y branch. And once I convert that, now this load impedance is going to be in series with the line impedance. So that's the reason I'm converting it. At this point, I don't know, I mean, for sure, this 1 plus J1 is not in series with 12 minus J9 or not in parallel with the 12 minus J9. That's the reason I'm converting the delta into Y. So here I have a delta. Okay, so A, B, C, so ZAB, ZBC, ZCA. I'm converting this into a Y connection. Okay, so Y impedance. When I'm converting this into Y impedance, ZA, ZB, ZC. Okay, now my goal is finding from here to here, finding ZA equal to, so ZA is right here between these two, right? So multiply these two impedances, so which is ZAB multiplied with ZCA over, add all three together, ZAB plus GBC plus GCA. Okay, so follow the same method to find ZB and ZC. So to find ZB, so ZB is right here. Okay, multiply these two impedances, which is ZAB times ZBC over AB plus BC plus ZCA. Okay, you can do the same thing for JC. Now here I have a balanced load. Okay, so if I have balanced load, so here 12 minus J9 times 12 minus J9 divided by 12 minus J9 plus 12 minus J9 plus 12 minus J9. So 3 times 12 minus J9. So these two get cancelled out. Okay, so can I say ZA equal to 12 minus J9 over 3? Okay, so the important thing is to convert this, as long as it's balanced load, all you need to do is just divide it by 3. Whatever the branch impedance of the star, delta divided by 3, that will give you the branch impedance of the load. This is going to be 12 divided by 3, which is 4 minus J3 ohm. That is the branch impedance. So remember, the branch impedance of the delta is ZAB. It's a big compared to ZA. That's how I remember. So delta impedance is larger than the star impedance. how many times? 3 times larger than the star. So here I have 12 minus J9. When I converted this into star, it is 4 minus J3. 12 divided by 3 minus J9 divided by 3. That's how we'll find the line impedance. So here what I'm going to do, I'm going to replace this delta load with the Y load. So when I redraw the circuit diagram, okay, here is my circuit diagram. So here I just indicated only one branch impedances, but you can clearly see since it's a balanced load, I'm not indicating the third one, or maybe I can do it 1 plus J1. Now I can clearly see these two impedances, 1 plus J1 and 4 minus J3, those two are in series. So I can add those two and say the total impedance is the total equal to 5 minus J2 ohm. So now for simplification purpose, I'm going to redraw. You don't need to do it in the exam or in the homework, but you can clearly see if I draw the circuit diagram. Okay, now this given voltage is 120 at an angle of 0. That's a line to line value. I have this value as 5 minus J2 ohms. Now I know line to line value, which is 120 at an angle of 0. Can I find the phase value? What is the phase value? It must be 120 divided by square root 3. That will give you the phase value. So VPH equal to 120 over square root 3. That value is 69.28. Don't worry about the phase angle there. Just take 69.38. Now I can find the current there. IPH equal to 69.28 over 5 minus J2. Okay, convert that into polar for R. I just need the magnitude, so square root of 5 square plus 2 square. That value is 5.38. 69.28 over 5.38. So IPH equal to 12.87 ampere. That is the phase current. One sign of phase current, I think it's a good idea to find the power factor. Cos theta S, source power factor. I'm finding the source power factor because this impedance 5 minus J2 is appearing when we look at the circuit from the source point of view. So this is R over Z. R I have 5 ohms and Z I have 5.38. That power factor is 0.929, so 0.93. It is leading power factor because I have minus J2. Here I can find the source power factor, load power factor, cos theta L equal to 4 over 5. 4 over 4 square plus 3 square, or I can write this as 5 at an angle of minus 36.86 degrees. So which is 0.8. This is also leading power factor. So load power factor is only 0.8, but when we look at the source, it is 0.929. Remember, 0.929 is always good power factor than 0.8. It doesn't matter whether it is leading or lagging. Now I have all the values needed to find the power supplied by the source. PS must be 3 times 69.28. VPH, I'm using VPH, IPH cos theta S. Okay, so 3 times VPH is 69.28, IPH is 12.87, cos theta S is 0.929. I have this value as 2485.96 watt. Okay, that's a power supplied by the source. And QS must be 3 times 69.28. 12.87 sine theta. So if I have cos theta equal to 0.929, find theta value. This value is 21.72. So sine 21.72, this equal 989.9 volt ampere reactive. So I have PS, QS, and source S is nothing but PS. That's a capacitive load, so capacitive load supplies QS, so it's minus J, so which is 2485.96 minus J 989.9 volt ampere. That's the unit for S. This is a complex power. You can convert that into apparent power, which is square root of PS square plus QS square. I mean, even though that's a negative number, I'm squaring it. When I square it, it will become positive. This value is 2675.8 volt ampere. That's SS. Now we can find the load, power consumed by the load, by there are a few ways. All I can do is I can find the current here, the current in the line. Basically, since I found the current in the phase of the load and it is a star connected, whatever this I phase must be equal to I line, isn't it? So what is the line current there? The line current there must be 12.87 amperes. Now from there, can I find the line losses there in the line? I can do that. So line losses equal to 3 times IL square times R line. Okay, so 3 times the line current is 12.87 whole square, line resistance is 1 ohm. That will give us the line losses. This is 4096.9 watt. Okay, those are the power losses in the line. So P load must be P source minus line losses. Okay, so that value must be 2485.96 minus 496.9. That will give us the power consumed by the load. That is 1989.04 watt. I can find Q line also by using the same formula, 3 times IL square. IL is the line current, line impedance XL. This is also J1 ohm, so I can use the 1 ohm, don't need to include the J. So XL is 1, IL is 12.87, this is 3, this is also 496.9 volt ampere reactive. Now Q load must be, now what kind of impedance do you have in the line? The line is, you have 1 plus J1, so that is a inductive load. So inductive load always takes that much power. When it comes to the load has capacitance. Okay, so basically Q load must be, see, when it comes to the source, this is you are supplying it back. That's the reason I used minus J. So this minus J indicates that because of the capacitive load, the source is supplying 2485.96 watts of active power. At the same time, it is receiving 986.9 volt ampere reactive via watts of reactive power. Okay, so that's the reason that's what the minus indicates. Okay, so the load is supplying it back how much? 989.9, as well as it is supplying this much, 496.9 to the line. So the total 1486.8 volt ampere reactive. So don't get confused. Basically, since the load is capacitive load, it is supplying this much, it is generating this much reactive power. Out of this, the line is consuming this much and the remaining is giving it back to the source. So to avoid confusion, most probably I would say take this as a negative, take this as a negative, so that will make it easier. So S load must be 1989 point, so this must be negative 2 if that's the case. 1989.04 minus J 1486.8 volt ampere. That's the S load. Now I'm going to draw the vector diagram. Vector diagram we always draw it for the delta load. Okay, so when you look at the delta load, so I have the line current as 12.87 amperes. So here you can go back here and you can say this line current is 12.87 ampere. Okay, so what is the phase current? It must be 12.87 divided by square root 3. Why did I choose this 12.87 as a line current? Here the line current is same as the phase current, right? Why shouldn't I pick, or why shouldn't I say it's a phase current and say the same as phase current there? I cannot do that because the phase current here, this is for a Y connection. When it comes to the delta connection, the impedance value is going to change, so the current passing through that impedance is going to change, but the line current will not change. That is the reason I'm choosing this as a line current. So the phase current here must be 12.87 divided by square root 3 of 7.43 amperes. So when we draw the vector diagram, we always draw the vector diagram for the load. So here is our load. I didn't calculate the exact angle, so I'm going to draw an approximate vector diagram. So here is a reference. So I'm going to choose this as my IA, IB, IC. To draw the exact vector diagram, I should have this angle. What is this angle? 7.43. Actually, I can get that angle right away. That angle must be theta equal to tan inverse of 9 over 12, and it's minus 9. So whatever that angle, that is minus 36.86 degrees. Okay, so this angle must be 7.43 at an angle of minus 36.86 degrees. This angle always comes from this impedance. Okay, so I can say 7.43 minus 36.86. So all I need to do is, as long as I know that angle, I can draw the exact vector diagram. So here is my IA. This angle is 36.86 degrees. Okay, and IB somewhere there, and then IC somewhere there. The phase angle must be 120 degrees apart. Okay, and here is minus IC, and here is our line current IL, and this angle must be 30 degrees, and here is our VA. I mean, the IC, you see that this exactly 90 degrees, but in reality it's not 90 because it should be around 84 degrees. Okay, 90 is somewhere there. This is our accurate vector diagram. Sorry for the long video. I'll stop this video here. I'll solve next example in the next video. Thank you.